Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing a very important topic, particularly these transition metal alkyne complexes over the last few lectures, and in the previous lecture we had seen about the techniques which are often used for characterizing these transition metal alkyne complexes, and what we had seen is that transition metal alkyne complexes can have two forms of structure. One is a pi complex and the other is a metallocyclopropane kind of structure, and that these can be distinguished by various spectroscopic techniques like IR, NMR, as well as by X-ray single crystal diffraction techniques. So, these transition metal complexes have two kinds of structures. One is something of a linear pi complex type, or the other can be something of a cyclopropane kind of type, and that they have two structures which can be distinguished by various spectroscopic techniques. What we have also seen that these coordination or transition metal alkyne complexes lead to stabilization of various unstable alkyne. For example, these transition metal alkyne complexes stabilizes various unstable alkynes like halo substituted alkyne, which are explosive in free state, but stabilized when coordinated to metal. So, this is one. The others are kind of it also stabilizes cyclic alkynes, and in this category falls the cyclohexane, which is stabilized when coordinated to transition metal, and the stabilization comes from release of ring string, which this unstable cyclohexane possess. The same can be extended from cyclohexane to benzene, and then ultimately even further the same can be extended to benzadiene. So, what we see that these transition metal alkyne complexes we had discussed in our previous lecture has several utility, and among them one of the most useful utility is this type of complexes stabilizes unstable alkynes like the ones which are halogen substituted acetylenes, which are explosive in nature, but still got stabilized when coordinated transition metal, as well as the cyclic alkynes like hexane, benzene or benzadiene, which two are stabilized when in the transition metal complexes, and the stabilization arises from relief of ring strain, which the free cyclic alkyne are subjected to. So, with that discussion we had in the last lecture, we are going to discuss an important aspect of these transition metal alkyne complexes, particularly their reactivity in this lecture. Now, of the reactivity aspect, of transition metal alkyne complexes. And one important reaction is the hydride attack on an eta 2 coordinated alkene complex leads to eta 3 allyl complex. So, it is sort of like a hydride complex going to an allyl complex, and the transformation is given over here, where alkyne complex which is eta 2 alkyne when treated with BH4 minus gives this eta 3 allyl complex, which is kind of extremely interesting as to how does this conversion proceed. M dash. So, this conversion is proceeds through a sequence of rearrangement and intermediate steps resulting in such conversion, and we are going to look at the proposed mechanism for conversion of this eta 2 alkyne to eta 3 allyl in more details. So, let us take a look at the proposed mechanism that has been given for the conversion of eta 2 alkyne to eta 3 allyl. So, or this is CH3 and this is eta 2 alkyne when treated with BH4 minus, the hydride attacks at this carbon and gives a C CH3 H. So, this is a eta 2 vinyl complex. Now, that undergoes a rearrangement to give this eta 1 vinyl. So, eta 2 going to eta 1 vinyl, which undergoes another rearrangement to give metal hydride. So, this becomes eta 2 allene. Now, this eta 2 allene undergoes a rotation along this MC bond to give this CHR complex, which undergoes again. So, this also is a eta 2 allene. Which undergoes a rearrangement to give M dash CH2 CH CR H. So, this is eta 1 allele. Finally, to give this CH2 CH CR H M dash, which is a eta 3 allyl complex. What one can see that these conversion of an eta 2 alkyne to an eta 3 allene proceeds by several rearrangement and several step, eta 2 alkyne going to eta 2 vinyl, going to eta 1 vinyl, going to eta 2 allene, then that goes to another eta 2 allene, from there it goes to eta 1 allele, eta 1 allele to eta 3 allele. So, these are a very complicated series of maneuver that sort of eventually leads the conversion of eta 2 alkyne to eta 3 allele, and this reaction is unique for transition metal alkyne complexes. Now, this is a very common phenomenon, and there are a lot of applications arise out of these rearrangements, and then we are going to take a look at this particular intermediate, which is how does the eta 1 vinyl and eta 2 vinyl compounds they sort of interchange among each other. So, we are going to now take a look more closely at this eta 1 vinyl and eta 2 vinyl complexes and their canonical forms. So, C H C H, this is eta 1 vinyl alpha and beta carbon, and the corresponding eta 2 vinyl structure can be given as M C hydrogen C this is alpha beta eta 2 vinyl. This structure eta 2 vinyl is formed from the metallocyclo or called metallocyclopropene structure, where this is formed can from the metal to ligand back donation, and that results in significant downfield shift of the carbon center. So, these the difference between these two form can be assigned based on 13C NMR spectroscopy and the assignments. And so, this is the eta 2 vinyl form is more like a metallocyclopropene intermediate, which is formed by back donation of the metal electron onto the pi star orbital, resulting in this eta 2 vinyl intermediate. Now, this eta 2 vinyl intermediate is a very important intermediate in the conversion of eta 2 alkyne to eta 3 allele, as we had seen in the earlier transformation. These transition metal alkyne complexes can be converted to various kinds of compound depending on the reaction, and a very nice example is given. TM alkyne can be converted to eta 1 vinyl and also Tm carbene complex depending upon conditions. And the example of this is given below. So, Cp molybdenum, P OMe3, 3 P OMe3, alkyne C hydrogen TBU plus BH4 minus gives this molybdenum Cp P OMe3 P OMe3 this is eta 1 vinyl complex H TBU, which at 80 degrees centigrade eliminates P OMe3, giving the carbene complex MO P OMe3 P OMe3 C H2 T butyl, which is the carbene complex. This one is eta 1 vinyl complex and this one is eta 2 alkyne complex. So, what one can see is that depending on the reaction condition, one can go from eta 2 alkyne complex to eta 1 vinyl complex to carbene complex, and here is a very nice example how the same is formed with the elimination of POMe3. We are going to take a look at examples of this reactivity of transition metal alkyne complexes and reactions of alkynes with metal compounds can lead to di, tri and tetramerization. Of the acetylenic moiety. A very good example of this is PdCl2 plus 2 pH C C pH this cyclobutene with pH 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 PD Cl PD Cl Cl PD Cl pH 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 complex. So, this is cyclobutadiene fragment is formed. Cyclobutadiene fragment is formed from two of these acetylenic moiety, and this represents an example of dimerization of the acetylene in the reaction in presence of PDCl2. So, let us take a look at some more examples where this oligomerization takes place, and here is an example of trimerization reaction of alkynes, and this has been achieved by from kinetically labile cobalt complexes. So, kinetically labile cobalt complexes are known for cyclo-oligomerization of alkynes. So, here is a Cp cobalt olefin. So, this ethylene is the labile ligand, which when reacted with dimethylacetylene CMe gives this arene complex cobalt with methyl hexamethyl complex. So, this is a very nice example whereby this trimerization of methylacetylene to give this arene complex is achieved when methylacetylene is reacted with kinetically labile organocobalt compound, where the labile ligand is this bis olefinic moiety. Let us take a look at another such example of cyclobutadiene intermediate. So, isolation of butadiene complex from organocobalt complex. So, here it is a cobalt carbonyl reacting with Me3Si Me3, giving this cyclobutadiene complex of cobalt Me3 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 and Me3, which in presence of lithium in THF gives this anion dianion Me3 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 Me3. This is the dianion with two lithium coordinated at the top as well as at the bottom, stabilizing this, and this butadiene has equal CC bond length 149 picometer, and 6 lithium NMR shows strong shielding of 6 lithium nuclei that supports the presence of 6 pi electron as per Huckel rule. So, this is a very nice example where this aromatic 6 pi electron have been constructed from 2 acetylene by making the cyclobutadiene and then reducing and put more electron on this 4 pi system to make this 6 pi electron, and to stabilize that by lithium cation, not only by the X-ray, but also by lithium NMR. Such characterization has been done. So, with that let me conclude what we have been discussing and the part of the reactivity in today's lecture. We have started off by looking at these eta 2 alkyne transition metal complexes getting converted through the series of steps to give the eta 3 allyl complexes, and we have seen how that it goes through vinyl and allyl intermediates, and then we have looked into how these can be used for transition metal alkyne complexes can be used for preparing other organo-transition metal complexes, for example, transition metal carbene complexes, as well as transitional metal eta 1 vinyl complexes, and how they mutually can be converted one to another. We have also seen examples of isolation of cyclic oligomerized product, right from dimerization, trimerization to even the formation of aromatic cyclobutadiene 2 minus ligands having 6 pi electron by proper manipulation of the acetylene moiety by reaction with kinetically labile organo cobalt complexes. So, we have seen many examples of that, and that shows that these transition metal alkyne complexes are extremely versatile in being able to produce several other important and otherwise very challenging compounds. For example, this butadiene 2 minus having 6 pi electrons through proper manipulation. So, with that I would conclude today's lecture, and we are going to be talking a bit more detail in transition metal alkyne complexes, particularly their reactivity. The logical conclusion is that transition metal complexes are extremely important. They not only can stabilize various unstable alkynes by coordination to transition metal, but they can also participate in the very important reactions of oligomerization and dimerization, trimerization, or even oligomerization of substituted acetylenes to give products which otherwise are very difficult to synthesize as well as isolate. So, with that let me thank you for being with me in this lecture, and I am going to take up these transition metal alkyne complexes in more detail in the next lecture. Until then, goodbye and thank you.